Hi there, Science 10 and Chemistry 11. Today we're going to cover a lesson that really applies to both of you, Lesson 4 of the unit for Chem 11 and Lesson 2.1 for Science 10. Topic is energy and chemical reactions. I'm going to cover it to a bit of a different level for the two of you. In reality, I'm going to cover all of the relevant material for Chemistry 11. You in Science 10, I'd like you to pay particular attention to knowing what enthalpy is, recognizing an energy level diagram for an exothermic and an endothermic reaction, and knowing what an exothermic and endothermic reaction are. So I thought it would be really useful and relevant to start with an example chemical reaction. In fact, really two chemical reactions, one of which is more dramatic than the other. So I'll just get that going. So, not sure how well you can see me, but you'll be able to hear me. This is one I've showed you several times before. First of all, I'm going to bring something really close. It's this. It's the striker. So let's watch what happens when I grind it. Okay? There is, so far as I know, a very hard rock of some kind that is positioned here on the striker, maybe some kind of like a flint, and along the grating of the striker that you can hear, there's, I believe, probably iron. And so what's happening is I'm grinding it down by friction, and the iron is oxidizing in the air and creating that spark. That spark, you see me use it several times. You see me use it to start the Bunsen burner. If I didn't have this thing and I switched on the line for the Bunsen burner, what would happen? Well, I wouldn't be able to do my demonstrations, and the classroom would fill with natural gas, and that would be really bad. So we use a sparker to get the reaction going. I'm going to do that right now. So you saw, to be clear about it, that it didn't switch on. Didn't get going until I hit that with the sparker. Let's get this organized properly, and like that. Good. Now, I'm going to cover really portions of a lab that you've seen me do already, that you in fact did yourselves. Here I have some ice. Here I have some water. And I have a flame. I'm going to put the ice into the water. That's better. And of course, as you might expect, I'm going to measure the temperature over time. All right, it's not all out, no big deal. There's a bit of food coloring in some of this ice. It's not part of the demonstration, but that's fine. So let's stir this up a little bit and get this going. In fact, let's get the computer camera a little bit closer to that. So notice what we have here. We have a flame. That's very hot. You can see, or you will be able to see if I held the computer properly in the right angle, that it's so hot that it's making the metal grating here almost red hot. There's a lot of heat being released in this reaction. That heat, we can think of this reaction, by the way, as a system. Chemistry 11, you should remember what is meant by a system. it's a topic of inquiry, something we might wish to investigate with a uniform phase. Go back to your definition for system if you don't remember it. Here we have another, what we can think of as a separate system. It has 3 phases of matter. It's got a solid in the form of the ice, a liquid, and there's gas that will be released from this. Currently, the temperature of this water, I'm getting 16 degrees Celsius. Those of you who did the phase change lab will probably remember that you really should get around 0 degrees Celsius when I'm stirring it in water, but hey, I've got a flame right underneath this, and the thermometer probably as well. The glass of the thermometer is being heated up as well. You might call that a source of experimental error. And at this point now, the temperature in the thermometer has gone up to 18. Just over that period of time, the temperature has increased. Now we're at 19. We're going to let that run for a while. Great. Okay, good. Still going. All right, so again, to review, we have a reaction that's releasing a lot of heat. It is, and above it, we have a beaker with ice water in it. The ice water has 2 states of matter that are within that water. We have solid water, and we have liquid water, and a lot of heat arriving into that beaker. At this point now, temperature has reached 23.5 degrees Celsius, just as I've been talking. At this point, just so I don't get distracted from it, I'm going to show you some of the notes that apply to today's lesson, and I can go back to them, but I'll only have to carry the computer to them once. And you can use these notes preparing for any kinds of tests or assignments that you should have to do. So, Science 10 and Chem 11, this really applies to you. What it says is, energy is stored in chemical bonds as chemical potential energy. And that energy can be released as heat, which you are seeing now. We know that in molecules there are bonds, molecular chemical bonds. You need energy to break those bonds. And if enough energy is added, we call that activation energy. You should both know EA, activation energy. The bonds can be broken, and a new substance, the bonds will be broken, and a new substance can be formed if there are, for example, other substances for it to react with, or it can decompose. New substances can be formed under those circumstances. I noticed that I put will and can. What happens in a chemical reaction? I'll read this to you in case my writing is not perfectly clear. The shape, length, and number of bonds may change. Also, chemical energy may be released as thermal energy. That is called an exothermic reaction. Science 10, this word is not in your textbook for the old curriculum, but you should know the concept of an exothermic reaction. Or thermal energy or other forms of energy may be absorbed for a reaction to proceed. That's called an endothermic reaction. For endothermic, think energy in. For exothermic, think energy is exiting. A substance, in this case, with a higher chemical potential energy is being created. That's what I've written there. Here is a key learning piece, and so I will focus on that now, and I'll come back to it later. The energy level diagram. Here we see 2. This is an energy level diagram for an endothermic reaction. I would like you to note our axes. First of all, the x-axis is Progressive reaction. You can pause this video now and write this down if you want. I'll go back here. The x-axis is the progressive reaction. And you might think, well, that's equivalent to time, and I mean, it is really, because reactions happen over time, but really the variable of interest is that reaction progressing from a reactant side to a product side. Let's go back here to make sure you get this as well. This here, like that, good. This is an energy level diagram for an exothermic reaction. For an endothermic, you might note we started low and we went high. This is crucial for you to know. Here, for an exothermic reaction, we started high and we went low. Notice this as well. Notice these arrows next to the endothermic. Notice where those arrows are going. We have energy that is entering the system. And for an exothermic reaction, energy is exiting the system. Exiting the system into the surroundings. Now, in any chemical reaction, I say, yes, the shape, length, and number of bonds might change. And you can actually demonstrate this just by reviewing a chemical reaction, what you know about that chemical reaction in your mind, and if you know a little bit about the molecules, you can actually count the number of bonds that are made and realize that, yeah, often the number of bonds might change. We're rearranging the atoms, and that can change all kinds of factors. It can change the number of bonds, the shape of those bonds, how long those bonds are, often changes, and you'll sometimes get what are called double bonds, as well as just simple single bonds. And I'm going to give you an example of that based on this reaction you see behind you just now. Temperature, by the way, has now reached 51 degrees. So it's getting hot, and it's getting hot fast. Now, energy level diagrams, again, that's a key concept you should know. And I'll continue going through those axes. So your x-axis was the progressive reaction. A reaction happens over time, so it might be measured as a passage of time. The y-axis is a variable you probably never heard of. The y-axis is, you could think of it as being called chemical potential energy, but a chemist does not know it as chemical potential energy. They know it as this word right here, enthalpy. I'm going to write it over here just to make sure we have the correct spelling. Zero in on it and then erase it. E-N-T-H-A-L-P-Y. E-N-T-H-A-L-P-Y. Enthalpy. A word that you haven't heard of, that you can think of as chemical potential energy. The symbol for enthalpy is the letter H. Think heat. Now, it might be counterintuitive to call it heat because just because something, say, a stick of dynamite has high enthalpy, can release lots of reaction and an explosion, it's not like the dynamite's always hot. But in that explosion, heat can be released. And that's why, at least to my knowledge, H is being used as the symbol for it. Coming back to those energy level diagrams, let's consider again those axes. H, enthalpy, is on the y-axis. I'd like you to notice what happens in an endothermic reaction, because we'll start with that. In fact, I'm going to start my discussion of those with this right here. Many of you have noticed this on the windowsill. This is a jade plant. My Science 9 students and I, back in the fall, we began that chemical reaction. You might think, well, it's just a plant. You just started growing a plant. Yes, but we initiated a chemical reaction when we did that. Notice that where it was stored. It had to be stored by the window, where there is a steady source of light from the sun, a source of radiant energy. By the way, the temperature in here has now reached 65.5. It's continuing to increase. Notice then, again, that in this endothermic reaction, our chemical potential energy, enthalpy, starts low and it goes up high, and we have a kind of a bump in the middle. That bump is really important to understand. And then it goes down again. But having gone down, it's still at a higher point than it started at, which intuitively you would expect. In an endothermic reaction, we're putting energy into that system. That energy initially is being used to break bonds, but then new substances are formed, and those substances have higher chemical potential energy. But you can't get something for nothing. We had to put energy into the system in order to create the chemical potential energy. The chemical potential energy is higher for your products. I show the J plant because there is there's an endothermic reaction, and that reaction you've heard of is called photosynthesis. In photosynthesis, we're starting with very simple components. We're starting with carbon dioxide and with the water that in this case can empty from the Erlenmeyer flask. In the presence of sunlight and by the use of pigments that can capture light energy, chlorophyll, you might have heard of that, the simple compounds, carbon dioxide and water, can be rearranged. You're not making new atoms, you're not destroying atoms, mass is conserved, the atoms are just rearranged to create oxygen, which is a waste product, very useful for us when we breathe, and sugar. The product of photosynthesis is sugar. And again, from your personal experience, you probably know that sugar is a high energy molecule. If you've ever cooked with it and put some sugar into a high heat situation, maybe accidentally you happen to do that, you burn it, or maybe you caramelize it and you get a bit of smoke. You know that sugar has a lot of energy in it. Of course, you know you eat sugar all the time, or different things that contain sugar. And when you do that, we say our body's getting energy from the carbohydrates that are in that sugar. In an endothermic reaction, the products of the reaction have higher chemical potential energy than the reactants. We're going up. But what about that point in the middle? For the exothermic and the endothermic reactions, always notice it doesn't just go like this. It goes like this, with a bump in the middle for endothermic, for exothermic, bump in the middle, and down. That is shared in common by those two types of reactions. What we have there is called activation energy. Remember that with the sparker, I was able to strike this and we got sparks coming off. The methane didn't start burning until I ignited it with this. The activation energy is the energy that's required to start breaking those bonds and for the reaction then to proceed. In this case, there's a fairly low activation energy for burning methane. And also notice this, when I did that, I don't have to keep standing here with the sparker all the time. I can back away because once I get the reaction going, it's creating its own energy. And that energy is enough for the reaction to continue over time. How can I put it? It keeps itself going. It was a word I was looking for. It promotes itself. You see here, the heat of this water now is 84.5 degrees Celsius. It keeps going up. A very common mistake for students starting out in chemistry when they're drawing energy level diagrams is I say, hey, give me an energy level diagram for an endothermic reaction. A very common mistake is students would be like, well, I guess it's all about heat, isn't it? And so in an endothermic reaction, we needed heat to get that going, and so we start here and go down. No, that is a mistake. It's a mistake because in an endothermic reaction, what's being measured on that y-axis is chemical potential energy. In an endothermic reaction, our product has higher chemical potential energy than our reactants. But what about that middle again? That's where I lost my train of thought. In the middle, you've got what are called reaction intermediates. These are very high energy, very unstable substances that that go between the products and the reactants and the products. So these are substances which would never exist on their own as long as there are products to be formed from them, or we can go back to reactants. If we don't quite get high enough, that's going to happen. The intermediates don't persist on their own. When you're at the top of that energy level diagram, the top of that bump, there's only one way to go, and that's down. If you reach that activation energy, you go down to form those products. In actual practice, what are the intermediates? Well, they're very unstable particles that don't follow the bonding rules of chemistry. The simplistic way to think of the intermediates would be to say, well, everything's made of atoms. Atoms are being rearranged to make the reaction happen. And okay, I guess the intermediates are just the individual atoms isolated from all others. In the example I show you, I'm going to give that, I'm going to make that assumption, which is not necessarily accurate, but is a useful assumption to make for describing this conceptually. I'd like to go to the exothermic reaction next. So again, let's look at this here. In an exothermic reaction, we start high and we go low. Otherwise, the shape is similar. And again, notice this. Energy is being released to the surroundings. Two processes going on in that water that's boiling right here, middle screen. Middle screen, I guess. One process is a chemical reaction that is exothermic. I'm talking about the combustion reaction of the methane, of the natural gas. The other is a physical process. We know that boiling water is not a chemical reaction. It's a physical process, but it's still endothermic. It's an endothermic physical process when you're boiling water, because after all, it won't happen spontaneously until energy is provided by the surroundings. In this case, the energy is provided very efficiently by this flame from the Bunsen burner. So really here we've got these two systems. The flame of the methane, and then what's going on in the cup right here. Temperature is now reached, where is it? Just about 100 degrees Celsius of that water. Water is just about boiling temperature. Energy has been released as heat here. What happens here, in fact, what's pumped through is we've got methane gas with high chemical potential energy. I sparked that methane gas, provided the activation energy to initially break those bonds. That created those reaction intermediates, which could then form the products, carbon dioxide and water. The same stuff gets made when you burn natural gas. And here, in this physical process of boiling water, we begin with water in a liquid form as I don't know if, maybe we shouldn't call it a reactant, as the substance you're starting with, and we end up with water in a gaseous form. Energy must be provided for that to happen. So those are the concepts from this board I wanted to look at here. Again, endothermic reaction requires energy to proceed. Exothermic reaction, energy is being released. There's one more thing I want to mention about this right here. You might ask yourself, well, how is it that plants can do that at all? It looks like there's a very high activation energy for those sugars to be created. And there is. The answer, to a large degree, for plants is that what they have is called a catalyst, although in biological terms we'll call it an enzyme. It is a substance that lowers the activation energy. That bump in the middle, the top is not so high. Our reaction intermediates are not quite so high energy. The activation energy is lower, and this means that the photosynthesis reaction can proceed relatively more easily. I'll maybe get into that a little bit later. So, having covered those concepts, I'd like to kind of zero in a little bit on the combustion of methane gas. And here. So what I have here is combustion of methane, an exothermic chemical reaction. Being exothermic, we have that shape. We start high and we go low. It's an energy level diagram, so the y-axis is enthalpy, there, and the x-axis is the progress of a reaction, which might be measured as time. I'd like you to notice this right here, between my fingers there, like that. That is the activation energy. The activation energy, if I was to ask you to duplicate that on a worksheet, is going to be that vertical distance between the enthalpy of the reactants and the enthalpy of the intermediates. From the reactant side, how high is it to the top? That's the activation energy. And of course, you might have noticed back then, for an endothermic reaction, it's awfully high to the top. Endothermic reactions have a high activation energy. We go down here to get to the products. What are the reactants? What are the products? Here are the reactants. Methane and oxygen. I'd also like you to notice something I did here. This is a balanced chemical equation. We need one molecule of methane, that's the CH4 to make this happen, a carbon with 4 single bonds to hydrogens, and we have 2 oxygen molecules. 1 methane molecule, 2 oxygen molecules. Over here, we have our products right there. Carbon dioxide and 2 molecules of water. Notice this. 1 carbon atom, 4 hydrogen atoms, 4 oxygen atoms. 1 carbon atom, 4 hydrogen atoms, 4 oxygen atoms. This comes back to the law of conservation of atoms. But what is this right here? Delta H. That's something I haven't told you about. Delta H is the enthalpy of the reaction here. Our water's boiling. It's the energy change in the reaction between the reactants and the products. Notice in that exothermic reaction that we started high and we went low. There was a drop. For an exothermic reaction, we say that the delta H, the change in enthalpy, is a negative value. It goes down. Versus in an endothermic reaction, we start low and we go high. We're increasing the chemical potential energy. That's going up. Those of you who take physics, maybe you know this already. Those of you who don't, please be aware that when you have a triangle before a variable, what that means is the change. Notice as well, at arrow, it dropped. We started high and we went low for an exothermic reaction. The products, carbon dioxide and water, are more stable. They have more stable bonds. This makes them less reactive. We actually say that they have a higher bond energy. We don't mean that they have a higher chemical potential energy. The bond energy is actually a statement of how tight the bonds are. Notice something else here, that we have this carbon that is doubly bonded to an oxygen. As a general rule, double bonds are stronger, they're tighter, and as a result, the substances involved have a higher bond energy, lower chemical potential energy. We know that you can't burn carbon dioxide. You can burn methane. That's what's being shown right here. EA, right here. Again, that's the symbol we use for activation energy. So our new concepts right here are delta H for enthalpy as a symbol, and EA for activation energy. And in the middle, we have these unstable intermediates. They don't stick around very long, but you need to make them as part of the reaction proceeding. So, next thing I'd like to show you is, here it is. Let's see how this is going to show up. I'm going to do this like that. All right. These are molecular models, molecular model balls. In a molecular model ball, for them, carbon atoms are shown as black. I guess charcoal is black, so there you go. Hydrogen atoms, the smaller ones, are shown as white. Oxygen atoms are shown as red. Methane is CH4, one carbon bonded to 4 hydrogens. Oxygen is shown, we know that this is O2, 2 bonded oxygen atoms. The bonding rule for oxygen is it needs 2 bonds. The bonding rule for carbon is it needs 4 bonds. The bonding rule for hydrogen is it needs 1 bond. Let's look at what goes on in that reaction. Here are our reactants. 1 methane molecule, 2 oxygen molecules. Conceptually, I can tell you here are our intermediates. Yes, I have told you that intermediates can be other weird things like, say, just a carbon singly bonded to a hydrogen. For conceptual purposes and also for calculations, we call the intermediates single atoms. We'll get to why that is later. Oh, forgot an oxygen. There. Free atoms are our intermediates. These are very stable. After all, they want to bond with other substances to share their electrons. And here are the products. H2O is water, 1 hydrogen, 2 oxygens. There. It's not showing up very well. All right, high energy for those. 2 water molecules and that's better. 1 carbon dioxide. We started high. We went up to get to our intermediates. We're calling them free atoms here. And we went down. That drop between the reactants and the products is the delta H, the enthalpy of a reaction. And it is a direct measure of the amount of energy that's released in a reaction. In the case of that, the boiling water, the energy is being released as light and as heat. And that heat is used to drive the physical process of boiling water. There's one other concept I'd like you to see. Really, chemistry 11, this applies more to you. And that is this right here, delta HF. So delta H is a change in enthalpy, a change in chemical potential energy. The F part stands for formation. The heat released in a process, a chemical process, can be calculated from differences in heat of formation of the products versus of those of the reactants. So, this, by the way, as I've said before, is determined by the number and the types of the bonds. Carbon-carbon bonds and carbon-hydrogen bonds have higher enthalpy than carbon-oxygen bonds. What we do for calculating HF values or delta HF values, heat of formations, is you can actually express it in kilojoules per mole. What's a kilojoule? A kilojoule is a measure of energy. And what's of interest is the amount of energy that is released per mole of the reactants. In this case here, let's do this from a distance. Here's carbon. Here's oxygen. In this case here at the bottom, this is CO2. we've dropped a long way to get to CO2 because the chemical potential energy of CO2 is very low. But here's the key thing. From these reactants here, carbon bonding carbon to 4 hydrogens also releases some energy. It just doesn't happen to release as much. And here again we have oxygen. We can bond the oxygen to carbon dioxide, and we get that delta H value that's very low, that's very negative. Lots of energy is being released. Or we can bond it to water, and not as much energy is being released. Of course, we do know that in that reaction, the water and the carbon dioxide are being created in that reaction. Delta H values, heat of formation values for elements, for pure elements, are set at 0. They start with the pure elements and go down. All of the values in this case are negative. Heat of formation, delta HF values, are almost always negative. There's a few exceptions, a few of them are positive, but most of the time, when you're taking elements of the pure, atoms of the pure elements, and you're combining them to make compounds, most of the time, energy is released. The name for that is the heat of formation, delta HF, and it's expressed in kilojoules per mole. The field I'm talking about right now is thermochemistry. We're not going to get into that a whole lot, but a bunch of you are going to take a lot more chemistry courses as you go through your education, and so it doesn't hurt for you to have heard of delta HF. If you ever want to know these values, by the way, to do calculations, well, it won't surprise you if you can find tables of heat of formation values on the internet. So, I guess the last thing I wanted to show, and this isn't really crucial for knowledge just now, well, I'll show it to you just the same, is it's this right here. We have the thermal energy of water in the liquid form is lower than the thermal energy of water in the gas form. As energy is added to the system, that value increases. In fact, what's happening here is if we are, as there is progress, we go here from, here's water where it's all in the liquid form. We add thermal energy to that system that is the water. This is a physical process, not a chemical reaction. And we reach a point here where all the water has become a gas. The moment this water boils dry, we would say that the system, well, that system of water has now entered the classroom as a whole, and that water, having boiled, having become a gas form, is now at a higher level of energy, I guess until it condenses on the windows or whatever. And again, I just wanted you to notice that that's occurring in parallel with the energy released from the combustion of methane. Energy cannot be created or destroyed, only changed in form. Here we had a change in form from chemical potential energy. I provided activation energy to the methane. That created heat. The heat was released into the surroundings in this exothermic reaction. And then we initiated the endothermic process. And over time, this water initially began to simply increase in temperature. And that corresponds to this phase of that graph right there where it's going up. And then eventually all that water will have evaporated and we'll have gaseous water, which has a higher energy level amount per kilojoule per mole than water does in the liquid form. So That's all I want you to know for energy and chemical reactions. And again, Science 10, know what an endothermic reaction is, know what an exothermic reaction is, be familiar with enthalpy, and most importantly, be able to connect your energy level diagrams with the types of reactions. That's everything I want you to know, and I hope you found it useful.